Okay, chapter 3. We have discussed about hydrostatic forces on submerged plane surfaces and also on curved surfaces. So we're gonna look at an example on hydrostatic forces on submerged curved parts. Surfaces. So we have an example from again our reference Sangel. We have a gravity controlled cylindrical gate, a long solid cylinder of radius 0.8 meters is hinged at point B, and it is used as an automatic gate as shown in the figure. When the water level reaches 5 meters, so that is 5 meters from the ground, the gate opens by turning about the hinge at point A. Determine the hydrostatic force acting on the cylinder and its line of action when the gate opens, and the weight of the cylinder per meter length. So we are going to solve this problem for A, and you will refer part B. Okay, so when we try to solve this problem, the first thing that we need to remember from our previous discussion is that even if we have a pressure distribution along the curved parts, we are going to analyze the resultant force by projecting the force in the horizontal direction along the vertical plane, and we are going to project the force acting in the vertical direction along a horizontal plane, and we have to also analyze the weight that and we have to see how it affects how it affects the pressure acting on the curved surface. So here, as you can see, we have a vertical projection here, and we have the pressure distribution increasing downwards. You already know this, and we have the resultant force Fx along x direction, and you can see that it's a bit lower than the midpoint, and that is because the pressure increases as we go down. And the other projection we have is this horizontal projection. So we have a resultant force Fy, and you can see that the pressure is constant because it does not vary along the horizontal. So analyzing the horizontal component of the resultant force, we have Fh and Fx, and doing force balance along x direction or in the horizontal direction, you will have Fh is equal to Fx. So this is the x component of the resultant force, and this is the net horizontal force exerted by the pressure. So from this we know that that force is rho g HCA, and we have this assumption. It's not actually an assumption because we have atmospheric pressure acting on this side, and we also have atmospheric pressure acting on this side, and the two will cancel out. So you have horizontal force is equal to rho g HCA, which is equal to 1000, that is density of water, times 9.81 times 4.6. Now this 4.6 is the distance from the upper water surface to the centroid. Now this section is actually a rectangular section because the projection is into the page, into the screen. So you have a rectangular section, and the centroid of a rectangle would be halfway of the height. So you have 0.4 from this, you have 0.4, so you have 5 meters minus 0.4, you have 4.6, and the area would be 0.8 times 1 meter, that is the width of the gate. Okay, and yeah, so the horizontal force is 36.1 kilo Newton. And the vertical, for the vertical component, again we will do a force balance in the y direction, and the forces we have is Fy due to the pressure, weight of the water volume, and we have Fv. So if we take vertical direction to be positive, we have minus Fv plus Fy minus the weight, which is equal to 0. So Fv would be equal to Fy minus the weight, and Fy is equal to rho g hca. So this is the centroid for the lower projection plane, and again that is a rectangle, but this is horizontal, so the pressure distribution should be the same. So that would be at a 5 meter depth. So you have 1000 times 9.81 times 5 times area of this projection plane, and that would be 39.24 kilonewton. And as for the weight means mass times gravitational acceleration, and the mass is density times the volume. And so we have density, and the volume of this water column, water volume, is that if you take this, for example, let me try to sketch here. Let's take this part. So we have a square, for example, here, the size of the radius on each side, the size of the radius, and if we take the area of the whole square, and if we subtract the area of this quarter circle, we can get the area for this section. And if we get the area, we can multiply it by the length, and we can calculate the volume. So the area for the square is the radius times the radius, that is 0.8 squared, and the quarter circle, you have pi r squared, the area of the circle, over 4. So you subtract the area of the quarter circle from the area of the square and multiply it by the length, and you will get the weight to be 1.3 kilo Newton. So substituting the values here, you will get Fv equal to 37.9 kilo Newton. So the resultant force would be the vector sum. So this is the magnitude, this is the vector sum of Fh and Fv, and you will get the resultant force to be 52.3 kilo Newton. And to know the angle at which this force is acting, we can again calculate the angle theta by using this tan inverse of Fv over Fh, and that will be 46.4 degrees. So now we know the resultant force that is acting on this curved surface. And so check the answer to part B from the textbook, look at it carefully, and if you have questions, you can post in Google Classroom, or also send it in the Telegram discussion, and take this as a reading assignment. We have buoyancy and stability and fluids in rigid body motion, the remaining parts of chapter 3. So take a look at this, and I will have another discussion on this, so you can have a revision and a recap on these concepts, but I expect you to read these two parts.